All right, welcome back, everyone. So this is the final segment in the course on statistical network analysis here for Randomness. So in the next 3 lectures, I'm going to focus specifically on spectral methods and spectral properties of graphs. So Jesús and Keith in the previous lectures have built up models, methods, and ideas. And in the next 3 lectures, we're going to dive into some of those in more detail. Okay? So the first 2 lectures have a corresponding handout associated to them. You can download this now or tomorrow or whenever. It's available on my website, so you can either find me through Google or just type in this website directly. Under upcoming and recent talks, there's an IMPA hyperlink. Click that hyperlink and you'll have access to this PDF. Okay. This PDF is a handout rather than a collection of full lecture notes. The idea being that during the course of this lecture or in your own self-study, you can use it as a guide or a skeleton and fill in material. I've also included references here, so you can search for keywords to study this in whatever level of detail you want. Okay. All right. Rather than writing on an iPad, I thought I would try to scroll through this while keeping it large enough for you to see, use the blackboard because it's here. So I guess that's different from the previous lectures. Another thing that's going to be different from previous lectures is I'm going to actually ask you questions. And I won't proceed until someone answers. So we'll see how that goes. All right? In this handout, there are 3 sections. The first on spectral graph theory, we're just going to jump through very quickly. Today's lecture is focused on section B here, spectral clustering with graph Laplacians. The next lecture will be on spectral clustering with adjacency matrices. And then the third and final lecture of this mini course does not have an associated handout for it, okay? And so, and the very first page here for spectral graph theory, you'll notice this page is actually entirely blank, with the exception of the heading here, right? And this is deliberate, so in lecture we're going to fill this in a little bit, but you're of course welcome to sort of do this in your own self-study, right? So spectral graph theory has been around for a very long time, decades, and so we will sort of very rapidly build on sort of core ideas, but without going into all the details and the specifics. So at a very high level, the idea behind spectral graph theory is that we have 2 worlds. We have the world of graphs, and we have the world of matrices. Right? In previous lectures, in seminars that we've had at this event, there's been a lot of focus on graphs and their properties. What we would like to understand in the study of spectral graph theory is connections between graph theoretic properties and statistics and the corresponding properties of matrices and their factorization. So in particular, adjacency and Laplacian as the focus will be on in this talk. Right? Now, why might we do this? Well, there are a variety of reasons. When seeking to sort of compute or implement certain algorithmic procedures, it's often much easier to work with a matrix array for which we can apply a suite of existing linear algebra tools. So that's one aspect. At a very high level, we could think back to previous discussions about graph isomorphism, right? The question of when are 2 graphs isomorphic. Certainly an interesting question. In the context of graphs, we can think about when are graphs co-spectral, meaning that their adjacency matrices have the same multi-set of spectrum viewed as a multiset, right? So a weaker notion, but still a very interesting notion. To what extent does the spectrum of a particular matrix form characterize a space of graphs? or something like this, right? So this is really the key, key idea. A lot has been written about spectral graph theory. In these notes, I cite the book by Fan Chung. There have been chapters written in textbooks by authors including Dan Spielman. Brower and Hatcham also have a textbook, and so there's really a lot that you can find in the space of spectral graph theory. Okay. In our discussion, we are going to focus exclusively on symmetric matrices, right, which are going to be in correspondence with undirected graphs. We observe, okay? By the virtue of having symmetric matrices, they have an eigendecomposition that's very useful and stable to work with. Just briefly, can someone recall the concept of an eigendecomposition or spectral decomposition from matrix theory? Sorry? You have a bunch of eigenvectors, you have a bunch of eigenspaces, right? You have maybe expressions of this form, right? So you have particular subspaces spanned by eigenvectors. Pairs of eigenvectors and eigenvalues characterize certain properties of matrices. In the setting of symmetric matrices, we have the ability to decompose the matrix A into a product of orthogonal, diagonal, or orthogonal matrices, right? We can get an orthonormal basis for the whole n-dimensional space, right, with corresponding eigenvalues, and that's going to be very appealing and useful for our analysis, right? More generally, we have the singular value decomposition when we don't necessarily consider square matrices. Very similar ideas here. In this case, we have left and right subspaces. This distinction between SVD and eigenvalue comes up in a lot of recent work in statistics, particularly when the concept of your data matrix has a very drastic aspect ratio. You have, say, far fewer rows than columns, or vice versa, in which case the properties of your eigenspaces in certain statistical models where there's a notion of perturbation are quite different. Okay, but for us, we're going to focus on the symmetric case. And we're going to recall the, whoops, okay. So, right. So we have these, and now we're going to just briefly recall the operator norm, or the spectral norm for a matrix, right? That's the 2-2 operator norm on a matrix, but we can also think of that as simply the square root of the largest eigenvalue of M transpose M, giving us the corresponding singular values for a matrix M. Also the Frobenius norm, which has one representation as a square root of a sum of squared elements of the matrix, right? But we can also write it as a sum of the eigenvalues for M transpose M, then take a square root. Right? We also have the trace and the determinant functionals, right, for square matrices here. And the idea is that, again, for these quantities, there's sort of an entry-wise definition or notion and an equivalent formulation with respect to the eigenproperties of this matrix. Right? So in the case of trace, some of the diagonal elements, or just the sum of the eigenvalues of M, we have this Leibniz form of the determinant here, summing over permutations, but we can also write that as a product of just the eigenvalues of our matrix M here. Okay. All right. So spectral clustering with graph Laplacians. That's the key topic for today. This material comes largely from a tutorial on spectral clustering written by Ulrike von Luxburg, published in 2007 in the journal Statistics and Computing. I mentioned earlier Fan Chung's book, her 97 book on spectral graph theory. Also, I will briefly mention the textbook by Laszlo Lovász on large networks and graph limits. Okay. But just to set the stage for our discussion today, we're going to be using notation that's quite standard. We're going to let G be this tuple of a vertex set and an edge set. It's going to be our graph. The vertices or nodes we're going to write as v sub 1 to v sub n, or for simplicity, we'll also just write the positive integers 1 all the way through n. We are going to consider an adjacency matrix corresponding to a particular graph. We're going to think of this as weighted, so we're going to use W, and we're going to think of this as being a non-negative matrix. And so in particular, vertex I and vertex j are going to be said to be adjacent if the corresponding wij entry is non-zero. Otherwise, there is no link or edge between them. Okay. We have the degree of a vertex. Right? This is just the vertex I and looking at the weights in the adjacency matrix for all other nodes and summing this up. Right? And with this idea for each individual vertex, we can construct the diagonal degree matrix. Right? And that's just simply taking a matrix whose elements are, well, the 1, 1 entry corresponds to node 1, the 2, 2 entry corresponds to node 2, et cetera. Right? And so, I mean, we can even write these concepts using some linear algebra notation, right? So we have di. This is the degree for node I. So what we have is the matrix W, right? This is our weight matrix. We are multiplying this by the vector of all ones. This is giving us row sums. We just pick out the ith element of that. Right? And so now, similarly, we can think of D now in the notation as just the diagonal matrix constructed from the vector given by W1. All right. So in this set of lectures, we are going to be focused largely on the problem of clustering nodes in a graph. So we have to think about a notion of sets of vertices and partitions of our vertex set. And so we're just going to use the notation that A is a subset of V here, subset of vertices. Then the complement is just A bar. Right? We're going to use the indicator vector I sub A with coordinates f1 through fn to simply pick out elements in the subscript A and be 0 otherwise. And so here what I've done is I've written boldface 1 without any subscript. So in this case, this just corresponds to the vector of all ones. Okay, so we're going to say then that vertex I, so vi is an element of A, or even just I, that particular positive integer is an element of a set A. Okay. Given two subsets of vertices A and B, we're going to define the cut weight as simply the sum over all vertices I in A and J and B with corresponding weight wij. Right? Just summing over all these edge weights. Right? To measure size, we're going to use this vertical line notation here to just denote the cardinality of a set of vertices. And another notion of size for a set of vertices is also what's known as volume, right? So not simply how many there are, but now in terms of the degree for those particular vertices. So the volume of A is just the sum of the degrees for vertices in that group. Okay. So a subset A of vertices in our graph is going to be said to be connected if any two vertices in A can be joined by a path where all intermediate vertices are also in that set. Okay. A connected component is going to be a subset of vertices so that it's connected, but there are no edges between vertices A and its complement. Right? So all the edges, all the connectivity happens within the connected component. And then if we have a vertex set, a partition for that vertex set is just a set of non-empty subsets whose intersections are all the empty set and whose union gives us the entire vertex set. So just a partition in the usual sense. All right. So with these ideas, we can introduce our first matrix of interest, often called the unnormalized graph Laplacian. This matrix L is defined as the diagonal matrix of degrees minus the weighted adjacency matrix. Okay? All right, so we have a proposition here laying out 4 properties for this Laplacian. The first is that the quadratic form determined by this Laplacian has a particular expression where the quantity on the right here is just a weighted sum of square differences between the entries in this vector that we are left and right multiplying here. Proposition 2, or part 2, says the matrix L is symmetric and positive semi-definite. 3 says that the smallest eigenvalue is 0 and the corresponding eigenvector is just the vector of all ones. And 4 is that L has all non-negative real eigenvalues, with smallest being 0. Okay, so there's a little bit of redundancy in these comments, but we can sort of prove them all quite succinctly in one fell swoop. Okay, so let's sort of walk through in words how we would go about proving these properties. Right. So how might we approach the very first property here? That's right. Computation, right? Just compute it, nothing fancy, and we get this very nice simple expression. Okay, great. How about 2, showing that the matrix L is symmetric and positive semi-definite? I didn't say this was difficult, by the way. So if it feels simple or easy, that's good, right? This is sort of the starting point. Exactly, right? So by construction, I mean, by definition, D and W are both symmetric, so by construction, L is symmetric, and now we know that a property of positive semi-definiteness is that when we left and right multiply by vectors, that expression should be non-negative. And now if we look at what we established in bullet 1, well, that quantity on the right is a sum of a product. Each term in the product is non-negative. Right? The W is non-negative by definition. The square is obviously non-negative, and so this quantity is always non-negative, regardless of the input vector f that you choose, right? So we've proved part 2. Great. How about 3? That's right, exactly. So, I mean, if you notice that the vector 1, right, causes this expression to vanish, right? But the vector of all ones is also just an eigenvector for the matrix L that we started with, right? And so that gives us immediately that the vector of all ones is an eigenvector for the 0 eigenvalue. Great. Okay, how about the 4th bullet? Great, okay. So, and in particular, also, we know that positive semi-definite matrices have all non-negative real eigenvalues, and we all just established that one of them is 0, right? So, great, excellent. Okay. The next proposition is about the relationship between the connected components and the spectrum of the Laplacian. Okay, so let G be an undirected graph with non-negative weights. That's our present setting. The claim is that the multiplicity K of the eigenvalue 0 of L gives us the number of connected components, in the graph, and that the eigenspace of 0 is just given by the indicator vectors, where each indicator vector corresponds to the set of vertices in that connected component. Right. Okay. Well, we just saw in the previous slide that the eigenvalue 0, right, appears for the Laplacian and has some spectral structure. And we noticed that the vector of all ones is the eigenvector for that matrix, right? So maybe we can approach the second proposition by using this proposition and thinking about the case when we first have just one connected component and then subsequently generalize this to having k general connected components, right? So in the case when we have one connected component, right, that means any two vertices you give me have a path connecting them in that component, right? Okay, and well, in particular, we know that any two vertices are either adjacent or not, right? And so we want to guarantee then that connectivity has a relationship to this the sum that we have on the right here. Right, we want to argue that this has to be, this has to vanish, right, but correspond to connectivity in the vertice space. Right, so is it clear that if we have one connected component, then we have the vertex, we have the eigenvalue 0 with a vector of all ones giving us an eigenvector, and that vector of all ones is just identifying each vector in our each node in our entire space, right? If k is equal to 1, then we just have this relationship. Great. Okay. So how about the general case? And the idea now is to use the fact that we can write a Laplacian for our entire graph in the case when we have connected components in a block-structured matrix way. So if we have k connected components, the claim is that, well, without loss of generality, let's order all the vertices so that we first get those in component 1, then in component 2, et cetera, et cetera. If we check properties of the Laplacian, we indeed have this block structure appearing. And now we can appeal to, well, properties of block structure matrices, or if we really want, we can go back and sort of do an exercise using the previous proposition here now for each individual block, right? But the idea is that for this matrix, this block diagonal matrix, the spectrum of this matrix is given by the union of the spectra for these submatrices. Right? And when we look at eigenvectors, well, eigenvectors are going to have a block orthogonality property where they are going to vanish off of the component that we've specified. Right? So the vector all ones remains an eigenvector and denotes, in this example, still the first connected component. Right? But we have to zero out now all the entries of that vector for nodes not in this component. Right? So we have constant on this component, 0 all the rest, and the same idea for all these other blocks. So there's an eigenvector here that indicates or picks out these eigenvectors and is 0 on the remainder. Right? So, I mean, if we're willing to sort of believe that or check all the details, then what we've established is precisely that there's a correspondence between the multiplicity of the eigenvalue 0 and the number of connected components. Right? Why are we talking about connected components? Well, in some sense, we can interpret them as the simplest or easiest possible clustering setting, right? When there are absolutely no edges linking vertices in one component to another, right? So it's sort of a stylized, idealized version. everything we've been talking about here is deterministic, right? This is just for general graphs. Please.
So one thing is, why work with the Laplacian matrix? Like, from where comes the intuition to define the matrix in this way?
So for that, I would point you to Fan Chung's book. She goes into some detail about the historical developments. There are also connections to operator theory and Laplace Beltrami theory. So there are some connections in functional analysis. Here, we're just sort of taking it for granted that this matrix has some nice properties, and we're starting to establish, right, coarse properties of graphs and their connected components and eigenstructure of matrices. Right. But that's certainly a fair question. Any other questions or comments at this point? Okay. All right. Now, the term Laplacian or graph Laplacian is often very overloaded. Different authors can mean different things, and in particular, different definitions. I mean, the good news is that the most conventional definitions are all related in some relatively straightforward ways, but whenever you do encounter it, you should be careful to see what people actually mean. So the previous Laplacian we had, I believe, is sometimes called the combinatorial Laplacian. Here we have two other variants, the symmetric and the random walk Laplacian. Right? In particular, the symmetric Laplacian is just the original Laplacian we started with, but now conjugating on the left and the right by this diagonal matrix of degrees to the negative 1/2 on both sides. And then the random walk Laplacian is evoking the concept of a random walk on vertices in your graph. And we're looking at D inverse L. Obviously, this is only well-defined if the diagonal matrix of degrees doesn't have zeros on its main diagonal. So we're not going to go into the details here. This now just generalizes our earlier discussion, is sort of a nice little exercise to show for the symmetric Laplacian in property 1 of proposition 3, we again have this expression for the quadratic form determined by the symmetric Laplacian. Looks very similar to what we saw earlier. Now we have the square root of degrees appearing in some denominators, and that makes sense because we're conjugating on the left and the right by d to the negative 1/2. Not surprising. There are connections between the eigenvectors in these two cases. You can get to the eigenvector of the symmetric Laplacian from the random walk by multiplying your eigenvector by d to the negative 1/2 here. We're used to seeing the sort of the conventional or classical eigenproblem here, right? Ax equals lambda x, but the generalized problem is one in which we have ax times lambda, say, bx. Here, d plays the role of b. So the claim is that there's a correspondence between these eigenvectors for what's called generalized eigenproblem. Okay. Here, 0 continues to be an important eigenvalue for us, right? It continues to appear in the case of the random walk with an eigenvector that is constant or flat, right? And in the case of the symmetrical Laplacian, there's some weight or heterogeneity in that eigenvector's entries inherited by the degree properties of our network, right? All of these matrices are still positive semi-definite, hence they have n non-negative real eigenvalues. And all of them have the 0 eigenvalue with these vectors here. Okay. Any questions or comments at this point? Okay, just very briefly by analogy, we can establish a correspondence between the connected components of these new Laplacian matrices and their spectrum, right? So related to the proposition we just saw a moment ago, it continues to hold that the eigenvalue 0 indicates the number of connected components in these graphs, and the eigenvectors point to nodes in those individual connected components, right? So what we're seeing now perhaps is an incentive to study the spectrum or the scree plot of Laplacians, right, to determine how many clusters there are. And once we have that, then to look at the eigenvectors and to try to distinguish which cluster a particular, or which connected component a particular node belongs to. Now, in practice, if you have a graph consisting of sort of k connected components, it's not clear that you would want to work with them as a collection, right? Perhaps it's more interesting to work with each connected component individually, and then within that, even if it's only, say, weakly connected, to try to cluster nodes in that graph. And the idea sort of extends quite naturally. So if we're willing to think that small perturbations of this sort of idealized structure are still settings in which we can recover the true members, then that's the right approach for the statistical models that we'll see in a little bit. Right. Great. Okay, so another little exercise, if you're interested. We can take the symmetric Laplacian, right, and determine its eigenvalues now as a function of the number of vertices for a variety of traditional graphs of interest, right? So take the complete graph, the complete bipartite graph, a star graph, a path, a cycle, or a cube, right? This, for each of these graphs, right, given n, we have the adjacency matrix, and so we can think about what its eigenvalues look like. This is a great exercise from Chung's textbook. Okay, another little exercise. Take a graph G, undirected and simple, so now specifying that we don't have loops and we don't allow multiple edges. We have the symmetric Laplacian, which we defined a moment ago. For the sake of this example, let's order the eigenvalues from smallest to largest, and let's use this shifted indexing, lambda 0 all the way to lambda n plus 1. And so we have a few claims here listed out in this exercise, giving us statements on bounds of eigenvalues and their sums. And in fact, we've already done some of this, in particular, establishing the correspondence between 0 eigenvalues and the number of connected components in our graph. Okay. So in this discussion so far, we've taken G to be some graph that's been handed to us, essentially. We haven't yet had the ability to modify. We haven't talked about graph constructions at all. Now, in practice, it's often the case that given a data set, we construct a graph that reflects some connectivity properties, and then we do analysis on that graph. So I have just a few examples that I want to highlight here. So now if we think about a data set of n objects in some potentially abstract data space, and a symmetric similarity function. Let's call it little s. This maps x cross x into the non-negative reals. One task of interest could be to cluster data points using knowledge of their pairwise similarity. And let's write this just as S, Sij, and Sij is just this similarity function S evaluated at the corresponding data points xi, sj. Right. All right, I say similarity function here. In some cases, there's a reason to think of a dissimilarity and then to construct a similarity through the dissimilarity that you started with. But it's sort of easier just to work with this formulation here for now. So using knowledge of this, and so now a claim, so traditionally the process of constructing graphs to, quote, model the local neighborhood relationship between data points. Does it still show up if I write on this board? On the camera? Okay. Okay, great. So the most commonly encountered graph constructions, it's called the epsilon neighborhood graph. Okay. The idea is that we have, now I'm going to use A for adjacency. There is some epsilon quantity that governs the mechanism. So for an epsilon neighborhood graph, element ij of this adjacency is going to be given by an indicator of, now here I'm using d for distance, or dissimilarity being less than or equal to epsilon. And please, if something I write is not clear or visible, let me know when I will. Right. So we're simply identifying when the distance or discrepancy or dissimilarity between our two data points is no larger than some pre-specified threshold. Right. In this case, giving us a symmetric unweighted graph when considering a distance metric on our space capital script X. We also have a k nearest neighbor graph. Also symmetric, this time weighted. We're going to denote the graph's ij element here sub k as now taking the similarity for data points I and j times an indicator vector, where we ask that vertex I belongs to the k nearest neighbors of j, or that j belongs to the k nearest neighbors of I. right? If we want to be stricter and change this union to an intersection, then we get what's called the mutual k-nearest neighbor graph. And of course, there's the fully connected graph, symmetric weighted, and that's just the setting where we take the elements of our adjacency or connectivity to just be the similarity for the two data points that we started with. Right. So I mean, there are many examples that you might consider. Perhaps the most standard are so a similarity determined through a distance and threshold here. That is just the indicator that the distance is less than delta. The Gaussian kernel is also a popular choice. So with a bandwidth parameter sigma, this is just an exponential of a negative squared L2 norm when the vectors xi and xj are, let's say, just vectors in Rd. And of course, well, perhaps in the Euclidean setting, the most natural choice of distance is just to work with some conventional vector norms. So let's just take the Lpth vector norm for example. Right? So the moral of the story is that there are many different types of graphs that we could construct. Their properties vary. In practice, there's no one-size-fits-all mechanism. On the one hand, that might be disappointing. On the other hand, that might be encouraging because that means there's still new research and work to be done, right? There are jobs for us to gain and money to be made in the future. And I mean, each of these formulations is receiving a lot of attention, and in particular domains, in biology and the natural sciences, there are situations where you may prefer one choice or another. There are rules of thumb for how to choose epsilon and k in certain settings, but in general, there's still work to be done to understand how the choice of which construction, how the choice of construction influences sort of downstream analysis inference. In von Luxburg's survey paper, one of her subsections writes that this is still an open problem. This was in 2007, and I would say it certainly remains an open problem. There's been plenty of work since then, but there's still more work to be done to understand exactly how the choice here influences what you're able to deduce or discern from your data set. Right. Questions or comments at this point? All right. Okay. So here we are going to consider several different notions of cut or separation, if you will, given a partition of our underlying vertex set. Or more generally, just subsets of our vertex set. We already defined cut on an earlier page, right, as just summing over the weights in our weighted adjacency matrix for node I belonging to subset A and node J belonging to subset B. It makes sense to think now more generally across partitions of size k, right? And also to think of different sort of normalization or relative quantities rather than just absolute. So we have here what are the sort of the most conventionally observed. So we have this original cut weight between sets A and B. The cut of the partition whose elements are A1 all the way through AK. This is just summing over all cut weights of the AIs and their complement, and then accounting for multiplicity in the sum by taking this factor of 1/2. This is one notion. We can also normalize by the size of these sets or by the volume, right, being the sum of the degrees of elements in this set. Right? So from the cut perspective, using expressions like this, the idea is that to cluster vertices, we want comparatively fewer small connectivity between components, right, and large and frequent connectivity within the connected components. So we would like weights of the form that look at, AI and its complement. We would like these to be small. Right? Identifying our partition of the vertex so that there's a relatively small weight associated between vertices in those subsets. All right. So let's consider the case when we just have a partition of size 2, and we could ask the question, what about minimizing over subsets of vertices this ratio cut expression from the previous slide? And maybe let me just reproduce it here for convenience. This is in this case, this is just, this is K2. I'll just write in the general case. Right, so in this case, ratio cut, the ratio is normalizing by the cardinality of these subsets. Right, so this is our problem of interest. Okay. And so now to make the connection to the eigenstructure and analysis that we've been studying, in an effort to sort of reframe this problem, let's do the following. Let's define a vector Fi to have elements taking one of two values depending on whether Vi belongs to A or its complement. Now this construction, when we first see it, seems a little bit ad hoc, but it will turn out that there's a very good reason for doing this. Now maybe it's not so bad because we know from our previous discussion that eigenvectors were constant on connected components, right? So maybe the value doesn't matter so much. What just matters is that we're constant on one connected component, and here we're defining the same value for vertices in A. Okay, so that seems pretty consistent with what we saw before, and these are both going to be positive quantities for us. So really, forgetting about the magnitude, we have just a sign difference. Right? Okay, so maybe it's not so crazy to start with a construction like this. Then the observation is going back to our previous discussion. Right? This was not sort of just for the sake of doing it, but we can actually expand this expression here and show, after a little bit of algebra, that this is just giving us so for this vector, F transpose L, F is the cardinality of our vertex set times ratio cut. Furthermore, if we just sum over the elements in this vector that we've constructed, what we'll see is that we get cancellation. Right? So just a little bit of algebra, but some of the elements of this vector vanish. Right. Furthermore, the squared L2 norm is equal to n, the number of nodes in our graph, right, which is exactly the cardinality of V. Right. So what that allows us to do is rewrite this problem right. If we want to minimize this quantity, well, this quantity, so this is a non-negative quantity, this is a non-negative quantity. We have this expression here, this is always non-negative, right? So to minimize this, right, where this is held fixed, corresponds to just minimizing this expression, right? So we're reframing the objective function here, but in an equivalent way. So we're now minimizing this problem subject to the constraints that we've observed here, namely that this vector f is perpendicular to the vector of all ones, and that f in L2 norm is square root n. Okay, let's take just a moment to unpack this because it's maybe a little bit subtle. So we start with this ratio cut formulation, right? We're minimizing over subsets of vertices, okay? Now we're defining f, but notice that f depends on a, right? We've sort of hidden that. F depends on a, and f takes constant values on a and a bar respectively, okay, separated by a negative sign. For this expression, so f still depends on a, right? We have this non-negative quantity on the left, right? On the right here, this also depends on a, but only here in ratio cut. V, its cardinality is n, that's fixed, right? So minimizing ratio cut is equivalent to minimizing this over vectors of this form. F inheriting the dependence on a, right? So now, so subject to f as defined here, so with this f of a dependence, let me maybe write maybe it's clearer if I write f as f of a, right, depends on a, as well as, so if we have the vector of all ones, well, we're orthogonal to the vector of, if we have zero element-wise sum, we're perpendicular to the vector of all ones, and we have this norm relationship here. Okay, any questions about this development? Okay. So that's great. We have an equivalent way to think about this problem. However, the problem has not been made any easier because we still have a discrete optimization problem here through the fact that V is inheriting this dependence on A, right? A here is discrete. So we are going to relax the problem by removing this constraint, this construction here. So now rather than force us to look at vectors of this form, we're just going to look at general vectors, but now the minimization problem is now not going to have A. It's going to have min over F, which these are, for us, n-dimensional vectors. F transpose LF. Right? Any questions about this? Let's see. Okay. Well, this representation is now very convenient because we can appeal to variational inequalities and representations for eigenvalues and eigenvectors to show that solving this problem actually returns to us the corresponding, and I apologize, I dropped these conditions. Solving this can be done by simply taking the corresponding eigenvector of the Laplacian. Right, so we're still enforcing this constraint. Okay. I mean, this constraint doesn't matter much. What's really important is that we're orthogonal to the vector of all ones. And now remember that 1 is always an eigenvector corresponding to the eigenvalue 0 for the Laplacian. Right? So if that's the case, then we're looking in the orthogonal complement of that subspace. Right? That's going to give us the second leading eigenvector for the Laplacian. And then if we want to go back to the original clustering problem, which is to think about vertices, then we would threshold the elements of that vector. Say, take the positive ones to belong to one component and the negative to belong to the other. So just an entry-wise thresholding to get back to the original, right? If we just compute the eigenvector here, we're going to get numerical values on the entries, not necessarily just flat as we have here. Questions or comments at this point? All right. So these notes, this handout has a lot of space if you're interested in exploring this on your own further. So here we really just quickly ran through the k equals 2 case, but in general k case we can do something similar. We can construct a collection of vectors, right? We're then going to have a matrix product. So we're going to have a corresponding matrix called like capital F. We're still going to have properties of that matrix in much the same way here, right? So properties of its norm, and then we'll get an equivalent representation still with this sort of pesky relationship through the construction. It's still a discrete problem, and so then the relaxation will give us a minimization problem over. Now, we'll end up with a trace of matrix product, and we can still use the same tools from linear algebra to deduce that the corresponding vectors that minimize this expression are eigenvectors for the Laplacian that we're working with in general. Right, so there's plenty of space here if you're interested in this. Also, we could consider the normalized cut. That's where the normalization is by the volume, right? The degree is not just the cardinality. A very similar thing happens. In that case, we end up with the symmetric Laplacian appearing in the analysis, right? And so the punchline then for all of this discussion of cut is that if we're looking for partitions of our collection of vertices, so that we have relatively a small sort of weight for nodes between components, then the Laplacian eigenvectors are able to do that job, subject to the fact that we've modified the problem slightly. And we're not quantifying how close this solution is to the original solution because we're sort of throwing our hands up and saying, well, we can't really hope to solve the original problem, but hey, here's a relaxation that is seems reasonable and still leads to some useful approach for clustering. All right. Okay, so here's a great little exercise from well, inspired by von Luxemburg's survey paper. So there, she cites this paper from 1998, which considers the so-called cockroach graph. Okay, it's called a cockroach because the body would be given, I guess, on the far right here, right? And the antenna are up here. So this is a graph on 4k vertices determined by k here, and the question is, well, consider this graph, consider the partitions determined by the set A, that's v1 through vk, v2k plus 1 through vk. So that's all the vertices on this side here. So these vertices and their complement, A bar, versus B, which takes these vertices and then their complement down here. Right? So these are two different partitions. We can ask what are the cut and ratio cut values for these expressions. This is just to sort of practice the definition of these quantities. The reason for this example and treatment in this 98 paper is to better understand properties of the Laplacian and relaxation as well. So then there's a bonus after you do sort of the easy part. If you're sort of curious, you can numerically compute the eigenvalues and eigenvectors of the symmetric normalized Laplacian for this, for sufficiently large k. Let's say compare the findings to the previous exercise where we saw other graphs determined by a specified number of vertices, and then if you want, you can go back to the paper and investigate a little bit more. So. All right. Okay. This notion of cut, which we've been talking about here in a non-asymptotic sort of deterministic setting, is also relevant in the case when you have random graphs and when you think about large graph limits. So there's a textbook by Laszlo Lovász from 2012 studying large networks and their limits, in particular what are called graphons. Right? And the notions of cut appear there too. I wanted to just sort of briefly highlight that in this set of lecture notes. So we have the notion of cut norm and cut distance. Here we have norm sub hollow square. Okay, so this we claim is a norm on square matrices. Okay, just denoted by M generally, where this norm has a normalization factor depending on the size of the matrix, and you're looking at the largest absolute sum over entries Mij, I belong to S, J belonging to T, where S and T are subsets of the integers 1 through n. So this looks very similar to what we saw just a moment ago in our other definitions of cut. All right, I mean, here we see a max, but we're just defining a norm for the time being. Right? And so now one exercise is that for this norm, if we consider A to be a random matrix of what are called Rademacher random variables, so plus or minus 1, each with probability 1/2, then we can show there exists a universal constant C so that, well, it depends on your probability statement, I suppose, but there exists a constant C so that the cut norm of this random matrix A is bounded above by something that looks like n to the minus 1/2 with high probability. And the way to think about this here is that, well, the matrix A, if it's Rademacher plus or minus 1, well, there's some symmetry. It has expectation 0, so maybe there's reason to believe this norm should be small in a certain well-defined sense because there's not necessarily any structure, let's say, that you're trying to find. That's a very loose, very coarse idea, but so showing that this corresponding matrix is small. I mean, perhaps more interesting now, if we think about a random graph and its benchmark, we can define what's called the cut distance between two labeled graphs on the same node set here. Again, using this hollow square notation now, we have a distance given two graph inputs g and g prime. Again, with a very similar form, we're normalizing by the number of vertices. Here we're looking at a maximum absolute difference now between edges in graph G from these tuple sets S and T, subtracted from those corresponding to G prime. The idea being then quite nicely that we've just used the previous norm to define a distance in the obvious way. So this is just the previous cut norm of the adjacency matrix corresponding to G minus A G prime. Okay? And so now for this notion, we can think about a complete graph on n vertices, right? And now let's just prescribe that the edge weights are 1/2. We can consider the traditional Erdős-Rényi random graph, right, with edge probability 1/2, still on n nodes. And we can show, or the exercise is to show, that here the cut distance between this random graph and the complete graph on n vertices is going to 0 with high probability for large n. Right. Excellent. All right. So we've talked about the significance of the leading eigenvectors of the Laplacian, right? We've talked about how they identify a number of connected components. So now, in practice, what are we going to do for this problem of clustering nodes in our graph? I mean, pictorially, we have the following. We have a graph right? This graph gives us a matrix n by n. Now, what we're doing is we're taking a few of the leading eigenvectors. So we start with maybe a large n by n matrix. Now we have a tall, skinny matrix, right? N nodes, but k eigenvectors, right? And so now the idea is that, well, since these column vectors are flat up to sort of their magnitude and up to some potential orientation, if we look at all k leading eigenvectors together, then using knowledge of all the components should help us when trying to determine if two vertices belong to the same cluster or not. So in particular, these rows, right, give us now a point cloud in our k-dimensional space, right? And we may run a clustering algorithm, traditionally k-means. Let's say k is equal to 2. These are two terribly drawn sort of circles, right? And so procedurally, sort of this idea is now just spelled out in a variety of different algorithmic formulations. You could do this by just constructing the matrix or just using a matrix that you've been handed to begin with, but in this sort of common approach, we have a similarity matrix, right? We construct a graph from that matrix. Here we're working with the unnormalized Laplacian. We're computing its k leading eigenvectors. Supposing that we know the true value of k, let's say, then U is our matrix of eigenvectors, right? So U is exactly this matrix here. And now we're going to cluster the rows, traditionally with k-means, but you don't have to use k-means. You can use Gaussian mixture modeling with the EM algorithm or other approaches. And then based on the clusters that you get here, right, then you identify each vector here, the corresponding embedding, if you will, of the vertex to the original vertex in the graph, and then we would color the graph, say red or blue, according to what we observe down here. Questions about this idea, or this sort of pipeline, this logical flow? Please.
Is the process the same if you use another Laplacian version? Do you need
So there are some subtleties and ways that the story changes a little bit. So this is one commonly used clustering algorithm. The citation for it is in the von Luxemburg survey paper. Here are two others. Actually, these have citations, and it depends on the choice of Laplacian that you're working with. But the idea is fundamentally the same. So up to some like small modifications, you still take the leading eigenvectors, or say generalized eigenvectors. Here, conventionally, you still do clustering on the rows, right? K-means or something else. Now, there are other approaches. Jesús referred to this idea of projecting embedding vectors. So take vectors and project them onto the unit sphere, right? Normalize them. That's mentioned, in fact, here on the right. So we have a matrix T from our eigenvectors that normalizes the rows, right? Because in general here, this is an orthonormal matrix, but that doesn't impose any constraint on the row L2 norms. And so here we're projecting those rows to the unit sphere and then doing clustering there. Yeah. Great question. Other questions, comments? Yes.
Is there a standard approach to trying to find k?
There are popular heuristics for how to determine k, and in certain random graph models, people have developed consistent estimation procedures for estimating the true k. Right. So that is a nice segue into this figure. Taken from the von Luxemburg survey paper, which for a toy sort of simulation example shows a little bit of what's happening for different Laplacians when you look at the eigenvalues and eigenvectors. So here what we're doing is we are generating a data set, and our data set is actually given by samples here. These points themselves have some clear separation between them, right? But we are not going to cluster this histogram. Rather, we're going to form a graph. We're going to form, I should say, like a similarity matrix, right, using a Gaussian radiant basis kernel. And then for different choices of the Laplacian, we can ask, what do the eigenvalues and eigenvectors look like? And because of our choice of similarity, and because of how we've simulated these data points, the four sort of components that we observe here will lead to four sort of discernible components in the data matrix, right? So we're no longer in the idealized setting. There's still going to be a connectivity across these across these components, but we see something very nice. So we have the normalized Laplacian, where we're using the k nearest neighbor graph for a particular choice of k. We have unnormalized Laplacian. Here we have normalized, unnormalized with the full graph, right? So in the case of the full graph, right, where we're just working with the similarities, we observe a gap in the spectrum. Okay? And we observe a gap in the spectrum corresponding to the number of, let's say, weakly connected components in this graph. So there's a gap from 4 to 5, or perhaps 5 to 6. Here there's a gap from 4 to 5. Okay. These eigenvalues, so 2, 3, and 4, these are small though non-zero. Right? Whereas if we go to this k nearest neighbor construction, both the unnormalized and normalized have the first 4 eigenvalues being 0, right, or numerically indistinguishable from 0. And then the 5th eigenvalue pops out slightly. It's hard to see here, but it pops out and is now strictly positive. Right? So what we're seeing now in the simulation is that a perturbation of the stylized setting of having completely sort of disconnected components, we're still seeing the spectrum giving us information about k. Right? So you could define, if you want, some eigenvalue gap or ratio statistic, and then depending on whether you exceed or don't exceed a particular threshold, you could determine that, well, here 4 is the number of clusters. So our k hat, if you will. In statistics, we like to use a hat notation to denote an estimate or an estimator of some parameter of interest. We can also analyze the eigenvectors. Now, the representation here is a little bit harder to see, but basically, you can sort of divide up, for any particular eigenvector, you can divide up its entries and think about roughly like plateaus or approximate plateaus. And all combinations of these plateaus allow you to distinguish between the 4 communities. Right? So they're not exactly flat here, but I mean, the idea is that, okay, so the elements of this vector, so that these components are relatively small, then we have sort of a little plateau, if you will, here. We don't quite notice a plateau for the full graph, but we do have sort of separation away from 0, sort of above and below 0 here. Here, if we draw a line at 0, then we have points above and below, and we're seeing perhaps the cluster structure manifest here. So maybe I'll mention as a sort of a preface to next lectures that, here we're focusing on Laplacian eigenvectors and based on how we've defined them, the small eigenvalues. Right? In other situations, the large eigenvalues are actually going to correspond to approximate low-rank signal in your data where the signal has block structure and the block structure is interpreted as clusters or communities. So here, we're interested in small. Later, we're going to be interested in sufficiently large eigenvalues. And we're going to have to think about how noise and randomness dictates detectability of the number of clusters. Right? Too much noise is going to prevent us from being able to determine the true number of clusters. Okay. Maybe a brief practical note. So this discussion here is about k-means, largely for historical reasons. In practice, based on my experience and what I've seen in the literature and in the wild, people do like to use Gaussian mixture modeling with EM or some other approach. The reason being there you have criterion like BIC to determine, like BIC, right, to determine the number of components. So it's sort of built in for you rather than having to say choose a few values of k and run k-means. I mean, k-means, so we talk about k-means also a lot, but simply saying it is not the same as implementing it, right? In fact, you're never actually implementing k-means, sort of given its difficulty. Most often you're working with like a 1 plus epsilon approximation to k-means, which has polynomial time algorithms that can solve them. That particular variant is attractive in the context of statistics because we can relate it to what's called the Davis-Gahan theorem for subspaces, and we can rigorously prove statistical guarantees for 1 plus epsilon approximate k-means clustering, on top of the fact that we can actually implement it in practice. Whereas sort of k-means by itself, well, you can call it in R, in Python, in some functionality, but there's some random initialization under the hood. If you run it multiple times, you're not necessarily going to get the same output. Depending on the configuration of your points, it's not necessarily going to be that stable. In this lecture and this collection of lectures, we won't talk about the sort of the algorithmic or computational aspects, but it's something to maybe keep in mind if you move from theory to actual practice or implementation. Right. All right, so that's it for today. Next time we will discuss the adjacency matrix in certain random graph models. Thanks, everyone.